I'm Madison.
And I'm Logan, and our research has been over boundary effects on electromagnetic propagation.
So our research corresponds with the Ariana experiment, and Ariana is the Antarctic Ross Ice Shelf Antenna Neutrino Array, and essentially it's a neutrino detector in the ice, and our studies in sand mimic the electromagnetic propagation in ice. So we had to do a lot of supporting and initial research by testing a lot of antennas initially, and we used the VNA, or the Vector Network Analyzer, to characterize the antennas, and we did this using VSWR, which is the voltage standing wave ratio, and we tested horns, bicones, log periodics, and dipoles, and learned basically how each of those antennas worked. And we also tested antenna gain of the horns. Essentially, there was a possibility that some of the horns that we had could have 2 lobes of gain, and we tested it by rotating, essentially transmitting between 2 of the horns and rotating one of them at 15 increments of 15 degrees and mapping the gain, and we found that the horns actually had a straight lobe outcome.
So using those horns, we thought they could be initially we thought they would be a good fit to do an experiment. So we started by testing the sand, and the different grain sizes may have posed like an issue on if we could test it in fine sand or coarse sand. Maybe the signal would be different. So our first test was putting these antennas in the different sizes of sand to see how they reacted. So here we just, in the fine sand and the coarse sand, we put the antennas in. Well, it was one antenna doing the VSWR, okay? And we just put it in different orientations, and each line here is a different orientation. And there are a few outliers, but I think that's just because the connection wasn't very strong. When we had the antenna facing up, the cable going into the antenna wasn't connected very well. But not including those outliers, the trend is almost identical between the two. So we used this to determine that the sand wouldn't really matter. We could use the sand that we had on hand instead of having to find more of a specific type of sand. So another problem that those horns posed was that they were too big. So our container that we initially thought we could use, well, we wanted a larger container. We ended up going with a smaller container, and because of these limitations, we had to make smaller antennas. So we wanted to perform the tests at 4 gigahertz. So we used that. We calculated the length of the antennas, which was 3.75 centimeters wide and like 7.5 centimeters long. So we cut out some aluminum and made small antennas that would fit in the smaller container that we got. And these had a few cons. They were not very directional, and they were very flimsy and pretty feeble when we put them in the sand. So we ended up going to another design, which was the horn antenna. It just went. So with the horns, we had cardboard here that provided a constant flare angle, and also we were able to secure it with some nylon screws and some tape to make it more durable. But these were much better than the bow ties that we made because they were more directional, and also with the fact that they were more durable. But a problem that arose from this was that the wires could not be soldered on, so we had to connect them with the screws. So this connection was pretty weak, so we had to be very careful with the way the wires were attached to the antennas.
The reason that we needed our antennas to work at 4 gigahertz is because it had a much smaller wavelength, 7.5 centimeter wavelength versus a much larger one, so our container would be sufficient for that size wavelength.
So we did a few tests with our first antennas that we had, well, that designed with the horns. So the first test that we did was VSWR, and since we needed them to work at 4 gigahertz, we just used the VNA to get a reading at 4, and we pretty much deemed under a VSWR of under 3 as usable, and all 3 of our antennas at 4 gigahertz were in this usable range, so we knew that those were good to use.
Where's 3 on that? Can you point to 3 on that?
Oh, yeah, so VSWR, 1 is the best VSWR that you can have, and that's at the bottom, and each line going up is just 1, so
Okay.
1, 2, 3.
Okay.
So over here, past like 2, past 2 gigahertz, our antennas were usable. Another test that we did was the noise test. So we set up the antennas transmitting to each other, both plugged into the VNA, and we saw the so we plugged them in and had them in transmission mode to get a signal between them, and then we removed the antenna that was transmitting just to get a general background noise level to see what the receiver antenna would take in without the transmitting antenna. And we just found the difference between those two, so we subtracted the noise level from it. And this was to see if our antennas were enough above the noise level that we could recognize the signal and know that the noise wasn't affecting our reading. So they were transmitting in between 40 and 50 decibels above the noise level, so it was distinguishable from the noise. And another test that we did was beam width. So using the method that Madison said earlier for gain, we just rotated one of the antennas to characterize how far either way the antenna could perform with a significant signal. And that was 30 degrees either way with a 60-degree beam width overall.
So essentially all those tests that we were talking about earlier were preliminary tests for the final experiment. For our final experiment, we had 2 antennas transmitting and receiving, and we had the transmitter, one antenna in the sand, and then the other transmitter essentially rotating around, and I have a diagram here. So RX would be our receiver, and TX is our transmitter, and the receiver is actually below the sand level, and we had 2 cylinders that were made of PVC pipes that we essentially lowered the antennas into. And so we began with the transmitting antenna at 90 degrees, and we rotated it all the way down into the other cylinder, until at about 15 degrees it was at around the surface of the sand, and then at 0 degrees it was below the surface of the sand, and both of the antennas were at that level. So in order to decide at what depth we wanted to have the receiving antenna, we had to do another pre-experiment by lowering the antenna into the sand in VSWR mode until it stopped changing, which is when we determined it would be seeing a sand-only environment, and that was at about 15 centimeters below sand.
So past year we had to do a few calculations just to make sure that our experiment would work out. And the first was we used the Fresnel zone, and this was to find so we have, if this is looking down at the container of sand, we have our transmitter up here and our receiver antenna down here. And they're sending signal to each other, and there's an area on the surface of sand that is where they meet the surface of sand. And we had to, what this equation does is finds the radius of that circle, and we wanted to make sure that it was inside the bounds of the container, so we were seeing an all sand environment and no air. So using that equation, we plugged it in, and the radius was about 12 centimeters. Oh wait, no, never mind, sorry. Never mind. It's 12 centimeters, and our container is 50 centimeters wide, so it was no problem with the Fresnel zone. And another equation that we had to do was we used Snell's law, where our transmitter was, when you shine it through from one medium to the other, so from air into the sand, there's refraction. So when the incident passes through the surface of the sand, the angle that the receiver would have to be at is slightly different. So using Snell's law, we could just plug in our angle of our transmitter and determine what angle we had to have our receiver at to have the most direct path.
So we essentially did 3 trials of the experiment, and one was with smooth sand, and one was with a rough surface of sand, and then the final was with foil covering the top of the sand. And these were our results. So essentially what we found is that most of the angles where the antenna or the transmitter was in the air, they were fairly constant. And then when the antenna got to the surface level of the sand, we saw a little bit of an increase and slightly smoothing out. And then when our antenna actually went beneath the sand, this would be this orange on top, we saw a greater increase. And we saw this consistently. That was the first trial, and then we have the 2 other trials here where the turquoise again is at the surface, and then the orange is underneath, and then the white is at the surface, and then this orange is underneath. So we saw consistent results for each of the trials for that. And this is just a little bit clearer because we took out a lot of the more unnecessary information. And so here we have at 0, 45, and 90 degrees, so directly above, then halfway between, and then below the sand, which would be the red.
Can you point to the red, because we can't see it back here?
Right here.
It's like, yes, it's pretty high. Okay.
And these are, again, with the red, sorry that you can't really see it from back there, but the red is, again, coming up above the rest of the data. We also did a test where we continued to lower the transmitter beneath the sand, and we didn't see too much variation the lower and lower that we went with it in these separate tests, and we went down each time by 5 centimeters, so it's a 5 centimeter difference between each of those data.
Sorry, what's the difference between the divisions on the left and dB? Like how wide are the divisions? I can't read the numbers on the left.
Oh, okay. So this line is 54 and this is 76.
Oh, okay.
It's about 20 decibels between each line.
Okay, great.
A few obstacles that we had while doing the research. Well, the first main problem that we had was finding a tub to use. We originally wanted to use a cylinder that was 2 meters wide and 1 meter deep, but seeing as this was kind of unattainable, we settled for a smaller container that was about 1 meter long and 1 meter wide, 1 meter deep. So it was smaller, but it was what we had available to us, so we worked with it. Another main problem that we had were the cables. When we connected the cables to the antennas, they had to be stripped. And since we couldn't connect the stripped cable to the VNA to calibrate, we had to include these cables as a part of our antenna. So even though we can make our antennas almost identical to each other, they're going to be different because we didn't have similar cables to put on each antenna. So the antennas were changed quite a bit by these cables.
So finally, we have some suggestions for next steps. First of all, it's a larger scale study. Obviously, we had a really small container to work with, and if we had something bigger, we might be able to collect better data. Also, since our experiment applies to the Arion experiment, it might be better to actually use the medium that Arion is in, which is ice. Even though sand is meant to mimic ice, it probably would be more accurate to use what it actually is occurring in to find that refraction pattern or model. And then we would also suggest sturdier antennas because often our antennas would get adjusted a little bit or readjusted, and that would affect the pattern. And we would also suggest more intensive studies at the surface because that's not something we really focused on as much in our experiment, and I would suggest doing more of that. Are there any questions?
I don't know if you guys you probably didn't have look at this, at least quantitatively, but I'm wondering if you ever did the experiment where you had one of the antennas just on the surface and the other one in air. And so you have both antennas in air, and then you lower one of them until it just gets to the surface. Whether or not you saw a similar change at that point.
We didn't do
We
it
did
the
not
reverse
do that
way.
test.
No. We just did
We
it.
definitely would have if we had more time,
Yeah.
but yeah, we probably would have done more types of experiments, but we only were able to do the angled and then the depth, and then we just repeated it 3 times.
Yeah, so the whole time we had one of our antennas in the sand
Right.
with all the different configurations.
I mean, it's very suggestive and encouraging that you see this nice boost when you get directly to the surface. But if you see a similar boost when there's a transmitter in the air and the receiver is on that boundary layer, then that means that if there's any backgrounds floating around the air, they're also going to get trapped in the surface, which are going to mitigate any gain that you get from sensitivity in ice. In any case, that's probably, there was more time, that would be, whoever follows up on this, it's a follow-up experiment.
Anything else?
Anything else? Okay, thanks, guys.